Hello all, welcome back to Introduction to Atmospheric Dynamics. Here we're continuing our discussion on the applications of the basic equations in Chapter 3. Using the equation that we derived last time in Part 1, we're going to analyze the different flow regimes that arise from this balance that then pops up. This gives rise to what is known as balanced flow, or flow that arises because of balance between individual terms within the three-term equation of motion that we derived. So recall that this equation incorporates centrifugal force, Coriolis force, and pressure gradient force terms. Here the centrifugal force is described in terms of the square of the fluid's velocity divided by the radius of curvature of the flow. Recall the radius of curvature is a quantity that describes the curvature an associated circle would have in case it matched the same curvature of the fluid parcel. The Coriolis force here is simply F times the flow velocity, and the pressure gradient force is simply the negative of the derivative of the geopotential height field in the normal direction. Recall that the normal direction is always directed here to the left of the flow velocity. So the first question that pops up is, how does this generalize the geostrophic approximation? Recall that the geostrophic approximation pops up because of a perfect balance between pressure gradient force and Coriolis force acting in opposite directions. The pressure gradient force in this case is acting northward and the Coriolis force is acting southward. The purple lines here denote lines of constant pressure gradient force with pressure gradient decreasing towards the north. Because of the modification associated with the Coriolis force, which causes the fluid parcel to turn to the right, we must have that the fluid parcel is moving eastwards in order for it to be satisfying geostrophic balance, and consequently it is following along lines of constant geopotential. This balance arises in the case of zero curvature, where the radius of curvature of the flow becomes infinite and corresponds to a straight line motion. Consequently, the centrifugal force term drops out from the three-term balance relationship that we derived, and so we simply arise at a balance between Coriolis force and pressure gradient force. In natural coordinates, then, we can write this balance as Fv sub g, where the subscript g denotes geostrophic balance, is equal to negative di phi di n, or the derivative of the geopotential height field in the normal direction. Diagrammatically, we can depict the geostrophic balance for a case where the geopotential height contours are perfectly straight in the following way. The pressure gradient force in this case is directed up and to the left. The direction of flow for the fluid parcel is along lines of constant geopotential, and the Coriolis force is directed to the southeast. The pressure gradient force in this case can be approximated through a finite difference approximation, for instance using a distance depicted here over the red arrows equal to delta n. This delta n denotes a coordinate distance in the normal direction. Note that the normal direction in this case is to the left of the direction of flow. So for a coordinate distance delta n, we have a change in geopotential delta phi, and so the pressure gradient force experienced by the fluid parcel is then going to be equal to negative delta phi over delta n. Using the relationship for geostrophic balance that we had from the previous slide, we can then write this geostrophic balance as Fv sub g is approximately equal to negative delta phi over delta n. In this case, the real wind, or the real flow velocity of the fluid parcel, is actually going to be equal to the geostrophic wind speed if the geopotential contours are straight, again corresponding to the case of an infinite radius of curvature and no centrifugal force experienced by the fluid parcel. However, if the contours are not straight, then the real wind is not geostrophic. So let's break this up into two possible flow regimes. We're going to define cyclonic flow as flow around a low pressure system or flow around a geopotential minimum. This is associated, for instance, with flow around a tropical cyclone, extratropical cyclone, or around an atmospheric trough. On the other hand, anticyclonic flow refers to flow around a high pressure system or a geopotential maximum. This is associated with flow around an atmospheric block or an atmospheric ridge, for instance. So in the case of flow around a low pressure system, the circle that is associated with the curvature of the flow then is centered around the low pressure region. The radius of curvature is then associated with a normal distance that is positive. That is, the center of the circle is located in the same direction as the normal vector away from the fluid parcel. So curvature in this case then impacts the left-hand side of our expression. Now, instead of simply Coriolis force needing to balance the pressure gradient force, we have an additional term associated with centrifugal force acting on the fluid parcel. So in this case, when R is positive, we're going to have that the centrifugal force plus the Coriolis force together will balance the pressure gradient force experienced by the fluid parcel. Let's look at this in terms of the Ageostrophic wind. So the equation of motion that we had from the previous slide is our same three-term equation of motion in natural coordinates. We can split this into a geostrophic and ageostrophic flow, where the ageostrophic flow is defined as the difference between the real wind velocity, capital V, and the geostrophic wind velocity, Vg, that arises from the Coriolis pressure gradient force balance. Substituting in V equals Vg plus Vag then gives rise to the second line in this derivation. From the definition of the geostrophic wind here given on the third line, we can then write the ageostrophic wind in terms of the centrifugal force that it then experiences. So as we see from this expression shown here in blue, the centrifugal force is balanced by the ageostrophic part of the Coriolis force. So let's consider the case of cyclonic motion. From the previous slide, we had that centrifugal force is balanced by the ageostrophic flow, that is, the adjustment to the geostrophic wind needed in order to give the real wind velocity. Because flow is around the low, we have that the radius of curvature is positive. This means that the direction of curvature is directed towards the low in the direction of the normal vector. Hence, we have a sign on the left-hand side of this expression that is positive. That then must imply that on the right-hand side of this expression, we also have a positive sign. Since F is positive in the northern hemisphere, and we have an additional negative sign on the right-hand side here, this implies that the ageostrophic wind speed must be less than 0 or negative. However, since the total wind speed is equal to the geostrophic wind speed plus the ageostrophic wind speed, that must imply that the real wind must be smaller than the geostrophic wind speed. Consequently, the real wind is slower than the geostrophic wind when you are dealing with motion around a low-pressure region. This is analogous to what we pointed out in our last lecture about how the observed wind speeds did not agree with the geostrophic wind speeds when curvature was present. From a physical perspective, when we have no curvature, pressure gradient force is perfectly balanced with Coriolis force. These two vectors must have equal magnitude to one another. And in fact, the Coriolis force, you'll recall, is exactly proportional to the flow speed of the fluid parcel. However, when curvature is present, we have that the sum of the Coriolis force plus the centrifugal force will balance with the pressure gradient force. And so you must have that the real wind speed, which then determines the magnitude of the Coriolis force, must be weaker so that when added to the centrifugal force, you have a balance with the pressure gradient force. In each case, the pressure gradient is the same. Recall that we are imposing a pressure field that is independent of the flow itself. So in each case, regardless of whether curvature is present or not, we have the same pressure gradient force. However, with curvature, less Coriolis force is needed to balance the pressure gradient, and consequently, the flow velocity of the fluid parcel will be slower in the presence of curvature. This is observed in real life as well. Let's look at a few instances where we have flow around a low pressure region, here highlighted with black circles. You'll notice that in each case, the red wind barb, which denotes the observed wind, is weaker than the associated geostrophic wind speeds denoted here in blue. In general, the geostrophic wind speed tends to overestimate the observed wind in each of these regions. If we look more closer, for instance, at LZH, the lower part of this diagram, the observed wind speed here is 95 knots, and the geostrophic wind speed is 140 knots. This adjustment is particularly severe in this case because the curvature in this region is very strong for the flow. Let's now consider flow around a high-pressure region, or the case of anticyclonic flow. In this case, the circle that approximates the motion of the fluid parcel appears below the fluid parcel, or to the south of the fluid parcel, and is centered around the high-pressure region. Consequently, the radius of curvature, which is associated with the normal distance between the flow vector and the center of that circle, is going to be negative. That is, the pointing towards the center of the circle is in the opposite direction of the normal vector to the flow. So just keep that in mind then. For cyclonic flow, we have that the radius of curvature is positive, and for anticyclonic flow, the radius of curvature is negative. This is important in determining the impact of the centrifugal force on the fluid parcel. All right, for anticyclonic flow, with negative radius of curvature, the left-hand side of this expression will be negative. V squared will always be positive, so V squared over R must be negative in this case. This implies that the right-hand side is negative, and so in the northern hemisphere, where F is positive, we then must have that the ageostrophic wind speed is positive so that the signs of this expression are in agreement with one another. However, since the real wind is again equal to the geostrophic wind plus the ageostrophic wind, that implies that the real wind must be faster than the geostrophic wind for flow around a high. Again, from a physical perspective, we have, in the no curvature case, pressure gradient force exactly balances Coriolis force. However, in the case with flow around a high, the centrifugal force is going to be directed in the same direction as the pressure gradient force, so these two vectors are additive to one another. The Coriolis force, which is then directed in the opposite direction to the pressure gradient force, must balance the sum of the pressure gradient and the centrifugal force, and consequently must be longer than in the geostrophic flow case. So even though pressure gradient is the same in each case, the curvature force, which is directed in the same direction as the pressure gradient force, requires a stronger Coriolis force and hence a faster fluid velocity in order to maintain balance. Let's look back at our diagram for regions where we have flow around a high. For instance, highlighted here in the 3 black circles, you notice in each of these regions that the observed wind is actually faster than the predicted geostrophic wind velocities. Let's, for instance, look at YOY. In this case, the observed wind has a velocity of 30 knots, and the geostrophic wind in the vicinity has a velocity of approximately 25 knots. So again, this is consistent with our derivation on the previous slide. All right, natural coordinates in summary. We found a way to describe balance between pressure gradient force, Coriolis force, and curvature. So this generalizes the case of geostrophic flow by incorporating curvature in the flow. The curvature is then incorporated via a centrifugal force term. Note that this is a horizontal centrifugal force term, analogous, for instance, to the force an object might experience if you're, for instance, twirling it in a circle on the end of a rope around your head. We assumed in this case that friction was unimportant and only looked at flow at a particular level, so we fixed the pressure level at which we're performing our assessment. The pressure gradient force was then determined via a gradient of the geopotential field. We assumed the flow was constrained to these pressure surfaces and found that using natural coordinates, we could derive a simplified system and a simplified equation of motion to describe real flows within the atmosphere and explain why there was a difference between the geostrophic prediction of flow velocity and the observed prediction of flow velocity. So we can look at this a little bit farther in the case of balanced flow, and we can actually describe other flow patterns that occur at different scales and on different regions of the Earth. Let's first start by looking at cyclostrophic flow. This begins one of the three cases where we basically eliminate one of the terms from the three-term equation of motion that we just derived in natural coordinates, and we look at the force balance that results as a consequence of elimination of that term. The natural coordinate equation that we derived, it appears here at the very bottom of the slide, again incorporating centrifugal force, Coriolis force, and pressure gradient force. Cyclostrophic flow is the special case where we have negligible Coriolis force. Negligible Coriolis force often occurs in cases where the horizontal scales associated with the problem are very small. So, for instance, one might anticipate cyclostrophic flow to pop up in the case of tornadoes or dust devils, which have relatively small horizontal scales associated with them, but very large pressure gradients. Cyclostrophic flow describes steady flows where centrifugal force is balanced by pressure gradient force, and Coriolis force is largely negligible. So, in this case, the primary mechanism by which pressure gradient force is balanced for a fluid parcel moving in a curved region is through the centrifugal force. So in this case, this pops up again when V is large, and consequently you have a large V squared compared to FV, or in the case where R is small. So as mentioned, cyclostrophic flow tends to pop up for tornadoes and dust devils with high wind speeds and small horizontal scales associated with the underlying phenomena. So let's eliminate this term from the balance and then solve for the velocity experienced by the fluid parcel. Here we can multiply through by the radius of curvature and take the square root of the expression. Hence, the velocity experienced by the fluid flow is square root negative r times the pressure gradient in the normal direction. The interior of the square root must be positive in order for no imaginary solutions or no imaginary roots to arise from this equation. This implies that only two solutions are physically possible. Either the radius of curvature is positive and the pressure gradient force is negative, or the radius of curvature is negative and the pressure gradient, the derivative of the geopotential height in the normal direction is positive. Diagrammatically, these two look as follows. Either you have a direction of flow, which is in the counterclockwise direction as one might anticipate for typical large-scale flows around low-pressure regions. Consequently, the radius of curvature direction is pointed in the same direction as the normal vector to the flow, and it is balanced by the centrifugal force, which is pointed outward from the circle. So centrifugal force always acts outside, away from the circle, is attempting to push the fluid parcel away from the center. The pressure gradient force also is always directed towards the interior of the low, and this gives rise to a direction of flow which is counterclockwise. In the second case, the force balance is actually identical, but what flips is the direction of flow. Because the normal direction is then to the left of the direction of flow, or more generally is to the left of the direction of flow, then the pressure gradient increases as you move in the normal direction, but the radius of curvature in this case must be directed towards the center of the circle in order for this to be a physically legitimate case. So we actually end up with the exact same physical configuration in each case, except on the left-hand side you have counterclockwise rotation of the fluid parcel, whereas on the right-hand side you have clockwise rotation of the fluid parcel around the low. So interestingly, there's no preferred direction of the fluid parcel for the cyclostrophic flow case. This is contrary to large-scale flows where, if you recall, for extratropical cyclones, for instance, or tropical cyclones, which are relatively large-scale phenomenon, you always have, in the northern hemisphere, counterclockwise motion around the low-pressure region. However, in the case of tornadoes, which are dominated and described by cyclostrophic flow, you can actually have anticyclonic motion. The counterclockwise rotation associated with tropical cyclones and extratropical cyclones always appears when you're looking down on the object from space. In this image shown here, which is a picture of a tornado taken from the ground looking up through the feature, we see counterclockwise rotation looking up, which corresponds then to clockwise rotation looking down on the object. Hence, this tornado is actually an anticyclonic tornado. That is, the flow is clockwise about a low pressure region. So why can't we have cyclostrophic flow around a high pressure system? Let's consider the two possibilities for force balance that would be experienced by a fluid parcel if there was a high at the center of the direction of the stream flow, of the flow direction of the fluid parcel. So if our direction of flow, for instance, is counterclockwise around a high pressure region, centrifugal force is always directed away from the circle, so it is directed outward, and the pressure gradient is also directed outward. Because Coriolis force is negligible, we have no force in this force balance diagram which can counteract the sum of the centrifugal and pressure gradient forces being experienced by the fluid parcel. So this is an unphysical case of force balance. On the right-hand side here, we consider an opposite flow direction. In this case, again, centrifugal force is directed outward, and pressure gradient force, which goes from high to low, is also directed away from the high. Again, we basically have the exact same configuration of force vectors experienced by the fluid parcel, and so the fluid parcel will be ejected from the high rather than being in balanced motion around the high. So in each case, there is no physical solution that arises from the case of force balance. And so cyclostrophic flow requires that the flow be around a low pressure region. All right, let's consider the third case of balanced flow. So recall so far we've talked about geostrophic flow, which is balanced between Coriolis force and pressure gradient force. The second case, which is cyclostrophic flow, corresponding to the balance between centrifugal force and pressure gradient force. The last case involves a largely negligible pressure gradient, or more formally, inertial flow describes steady flows where centrifugal force is balanced by Coriolis force and pressure gradients are largely negligible. In this case, only the centrifugal force term and the Coriolis force term are retained, and this gives rise to a simple quadratic which has two solutions associated with it, one of which is zero flow speed, so capital V equals 0, which we're going to neglect in this case for being uninteresting, and a second solution which is that the flow speed is equal to negative f times the radius of curvature. Now, since the flow speed must always be positive by construction, we must have that in the northern hemisphere that the radius of curvature must be negative in this case in order to have a physical solution. So for inertial flow with velocity equal to negative f times the radius of curvature, we end up with a force balance diagram analogous to the one depicted here, with centrifugal force directed outward away from the circle and Coriolis force directed into the circle. The direction of flow is then clockwise around the circle. The normal vector here is then aligned with the centrifugal force vector. Inertial motion is always anticyclonic, that is, it's always clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. However, we can also, since the flow is circular, we can also derive an expression for the period of rotation associated with the fluid parcel, that is, how long it takes for it to complete one cycle around the circle. Since the circumference of the circle is given by 2 pi times the radius of curvature, and the period of rotation is just going to be equal to length divided by velocity, then by substituting in the expression for circumference of the circle and the velocity of the fluid parcel, we end up with a period that's equal to pi over omega times the absolute value of the sine of the latitude. Here, omega is the rotation rate of the Earth, and so is a fixed constant. Consequently, the period is purely a function of the latitude at which the inertial balance occurs. In fact, what we observe is that in general, the period is approximately 1/2 of a day for the value of omega, typical for the Earth, divided by the absolute value of the sine of the latitude. So you'll notice that because the flow velocity is determined by the strength of the Coriolis force, that as Coriolis force goes to zero, that as we approach the equator, the period of the motion becomes increasingly large. So the period of the rotation becomes large towards the equator and becomes small towards the poles. Let us now consider the general case of gradient flow, which incorporates all three terms in the force-balance relationship derived using natural coordinates. So far we've considered geostrophic balance, which is Coriolis and pressure gradient, cyclostrophic flow, which is pressure gradient and centrifugal, and inertial flow, which incorporates centrifugal and Coriolis. The three terms are often present within nature, and so we're interested also in the case where all three terms are relevant towards determining the flow direction. So let's start with our three-term equation from force balance. We'll notice that this expression is actually simply a quadratic equation in the flow velocity v. Again, we are fixing the pressure gradient field, or the geopotential field in this case, so it is prescribed in this equation and kept constant. We can solve this quadratic equation using typical quadratic formula and arise at a velocity v, which is given by the expression here. Simplifying this expression gives the expression for the gradient flow velocity shown at the bottom of this slide. Note that not all solutions are possible to this equation. Let's consider the possible choices which arise from different signs associated with the pressure gradient force and the radius of curvature. So we know that the solution v must be real and must be non-negative. By construction, we required that this velocity always be non-negative. Consequently, although there are 8 cases that arise from different choices of sign in the quadratic expression from the previous slide, 4 of these can actually be eliminated because they give rise to values of the velocity magnitude which are negative. 4 of these are actually physical solutions, and we'll refer to these as normal low, normal high, anomalous low, and anomalous high. In the normal low case, it's associated with a derivative of the geopotential field in the normal direction, which is negative, and a positive radius of curvature. For the normal high case, it is associated with a negative derivative of the geopotential height in the normal direction and negative radius of curvature. For the anomalous low case, we have a positive derivative of the geopotential height field in the normal direction and a negative radius of curvature. And in the anomalous high case, both signs are also negative. So the solution for low pressure fields then look as follows. On the left-hand side here, we have a normal low, and on the right-hand side, we have an anomalous low. The normal low is associated with a Coriolis force which is directed outward away from the direction of curvature, and a centrifugal force which is directed away from the direction of curvature. The pressure gradient force is directed inward towards the low. The sum of the Coriolis force and centrifugal force in this case must balance that pressure gradient force, and consequently we observe counterclockwise rotation of the flow around the central low. In the case of an anomalous low, we have that the centrifugal force is significantly stronger than the Coriolis force. This allows the Coriolis force to be directed inward and allows for the fluid parcel to be moving in an anticyclonic direction. In this case, the pressure gradient is again directed inward towards the low, along with Coriolis force, and these two are balanced by the centrifugal force directed outward. The solution for highs are given here. The left-hand side shows the normal high, and the right-hand side shows the anomalous high. These two highs are actually identical to one another, except for the magnitude of the centrifugal force relative to the pressure gradient force. For a normal high, the centrifugal force is much weaker than the pressure gradient force. This arises naturally from the case where you have weak curvature associated with the flow. The anomalous high case occurs when you have strong curvature associated with the flow, such that the centrifugal force is actually greater in magnitude than the pressure gradient force. In both cases, we have a pressure gradient which is directed outward away from the high, and this is balanced by a Coriolis force which is directed inward. Unlike the case for low pressure systems, the direction of flow is always clockwise. So what are the implications of this solution then? We know that the discriminant, which is the term that appears within the square root of the velocity solution for gradient flow, must be positive in order for stable solutions to exist. That is, we must have a real value of the square root and not an imaginary value for the solution to be physical. This then implies that the interior term must be greater than or equal to 0 or non-negative. There are then two cases that you can observe from that arise from this inequality. One is for the case of positive radius of curvature, in which case the derivative of the geopotential height field in the normal direction must be less than or equal to f squared r over 4. And in the case of a negative radius of curvature, we then have that the derivative of the geopotential height field in the normal direction must be greater than or equal to f squared r over 4. So this is a constraint that must hold for any steady flow, and it's a constraint that must hold on the pressure gradient field. If this constraint does not hold, then the flow cannot be in a steady, balanced state, and will instead fall apart and produce a more chaotic solution, or time-dependent solution. Okay, for the case of a normal low, let's consider how this inequality plays out. On the left-hand side, we have a radius of curvature which is positive. Direction of flow is counterclockwise around the low. Normal direction is pointed into the low pressure region and aligned with the radius of curvature. This is a typical normal low configuration. On the right-hand side, we have our normal and anomalous high, both of which share an identical configuration where the flow is in the clockwise direction about the high with a normal directed outward and hence a negative radius of curvature. For the normal low case, we have that the derivative of the geopotential height field in the normal direction is negative and the radius of curvature is positive. Consequently, we then have that the right-hand side of this inequality is always positive, whereas the left-hand side is always negative, and so the inequality is always satisfied regardless of the strength of the pressure gradient. In the case of a normal or anomalous high, both terms are negative, and so we actually have a constraint that then arises on the pressure gradient field in terms of the radius of curvature in order to maintain a steady flow. In fact, this constraint implies the absolute value of the derivative of the geopotential height field in the normal direction must be less than or equal to f squared times the absolute value of the radius of curvature divided by 4. If you consider now a series of concentric circles corresponding to fluid parcels which are rotating about the high as you get closer and closer to the center of the high, you will have a radius of curvature which goes to 0 as you approach the center of the circle. This constraint then implies that the pressure gradient must go to 0 faster than the radius of curvature goes to 0, and so provides an intrinsic constraint on the maximum strength of the pressure gradient as you approach the interior of the high. Consequently, high pressure regions must have relatively flat pressure gradients on their interior, which is not required for the case of low pressure regions. As a result, we actually have that normal highs tend to have slower wind speeds than normal lows, because the pressure gradient force is bounded and are typically then associated with fair weather. Normal lows, which do not have any such constraint, can have very strong pressure gradients towards the interior and consequently can give rise to strong storm systems. Hence, we claim normal lows are storms and hence normal highs are fair weather. Anomalous flows were not touched on in too much detail in this lecture, but they're not often observed in nature. For most large-scale motion, normal lows and normal highs are the dominant flow pattern. With that said, anomalous highs have been reported in the tropics, and they are a physical solution of the gradient flow equations. But anomalous lows, on the other hand, are considered strange and often not a useful approximation. However, with that said, they do appear in the case for very, very small values of the radius of curvature, such as in the case of cyclostrophic balance or tornadoes, as we've seen earlier in this lecture.